Good morning. Today, I will go through the contents of the learning guide number 2, which focuses on machine learning application for visual classification. This phase challenges us to connect theory and real-world application, showing how computer vision and artificial intelligence can be applied to solve practical problems in fields such as healthcare, renewable energy, assistive technology, and sports. What we need to do is remember that this learning guide has a value of 80 points. It has to be delivered by Monday, 29th of September. The detailed description of the activity, this collaborative activity focuses on the application of machine learning techniques for solving image classifications. The goal is to apply core concepts on feature extraction, data preparation, and monitoring that functional vision classifier prevalent to the intelligent IoT systems. These are the materials that are required for the development of this activity. All of them are included in the library of the university. This is the computer vision driver for wideband smoke recognition by IoT cameras. This is the vision mining of IoT-based data streams for advanced computer vision systems. This is the prominent solution for solar panel detection using a basic computer vision technology with IoT sensor in the solar panel manufacturing industry. This is an IoT monitoring system based on artificial intelligence image recognition and EMG signal processing for abdominal exercise performance. And this is the prototipo de comunicación audible a través del movimiento ocular con procesamiento digital de imágenes. They are all available in the library, so you can download accordingly to your needs. You need to follow these 7 steps. The must select a labeled image dataset. You have to preprocess the select dataset. You need to extract relevant features. You need to train a supervised machine learning model, any of them. Evaluate the model using classification metrics, accuracy, precision, recall, whatever it is. You need to compare the training model with at least one alternative configuration algorithm, and prepare the collaborative report, structured as follows. Introduction, methodology, exclusion, conclusion, and upper reference. So these are the particular guidelines for developing the learning evidence. The final PDF includes this, includes as well the source code and any supporting material using to develop this activity. These are any other rules you need to develop, but please consider that this is for yourself because we are only one member and the academic situation. I have prepared a small example of the document that I did. and I'm going to through this sample. This is my collaborative report for phase number 2 of the computer vision course. This study focuses on machine learning for visual classification, especially wildfire and smoke detection, using IoT-enabled UAV imaginary. As highlighted by one, wildfire in 2024, wildfire poses major risk to ecosystem and intelligent computer vision system integrated into drones can play a crucial role in early detection and disaster prevention. The dataset description. I use the CL5 UAV dataset introduced by one in 2024. It contains almost 20,000 images labeled in 3 categories: fire, smoke, and background. The dataset combines both real wildfire events and simulated controlled scenarios, ensuring robustness against environmental variability, such as seasonal changes and cloud patterns that can resemble smoke. This makes CL5 one of the most prevalent benchmarks for wildfire detection tasks. The methodology that I use consists of 4 main stages. The first one is preprocessing. Images were resized, normalized, and augmented through random cropping, flipping, and rotation. This step follows the recommendation of Martinez in 2020, who emphasized the importance of preprocessing and transformation in enhancing generalization. Number 2 is feature extraction. Classical techniques were used, including pixel intensity, histograms, canny edge detection, and local binary patterns, LBP, to capture textural patterns. Number 3 is the model training. We use, as a baseline, I implemented a support vector machine, SVN, trained on extracted features. For the advanced model, I use the visual transform-based FWSRNet, which leverages cell attention and contrastive learning. As one in 2024 demonstrate, transformer-based architectures can capture both local and global dependencies in images, making them especially powerful for subtle distinction in like smoke versus clouds. And number 4 is the evaluation. Following TOR in 2020, I rely on accuracy, precision, recall, F1 score, and confusion matrices as evaluation metrics. What I have for results. This result shows that the SVN achieved around 85% accuracy, but it struggles significantly with the smoke background classification. In contrast, the vision transformed based FWSRNet achieved around 95% accuracy, which with much stronger performance in recall and F1 score. As Singh in 2024 pointed out in the work on solar panel detection, transform-based vision models outperform traditional machine learning when high decision is required in complex visual environments. This confirms that my choice of FWSRNet provides clear advantages. What I have for visual evidence. My findings are illustrated with multiple visual evidences. The first one is fiber number 1. shows accuracy trends across training epochs where SVN stabilizes at a lower level, while FWSRnet converges toward much higher accuracy. I have included table number 3. The confusion matrix demonstrates that FWSRnet correctly identifies most fire and smoke samples, although some misclassifications remain. Figure number 2 illustrates a specific case of the error, such as smoke predicted as fire or plus misclassified as smoke. A common challenge also noted by one in 2024. Smoke as fire, cloud as smoke, background as smoke. And table number 4 summarizes precision, recall, and FP1 score metrics, showing that FWSRnet consistently outperforms SVN in all aspects. As a discussion, what you can say? The results align with broader trends in computer vision research, as stored in 2020, highlight traditional machine learning struggle to adapt to evolving and complex visual streams, while advanced architectures provide most robust solutions. Similarly, Jurado, Palma, and Figueroa in 2025, their IoT-based monitoring study emphasized how AI-driven image recognition can improve the precision of physical activity assessment. This resonates with the case where integrated AI with IoT enable UAVs makes real-time warfare monitoring possible. Furthermore, Singh in 2024 demonstrated in industrial context that attention-based model outperform conventional approaches in defect detection. This support our conclusion that transform-based architectures are better suited for subtle pattern differentiation, such as distinguishing smoke from clouds. Finally, Martinez et al. In 2020 remind us that preprocessing and careful future preparation remain critical, even with using advanced models. Without robust preprocessing, model can misinterpret nodes and features, reducing accuracy. As a conclusion, in summary, my work activity successfully demonstrate the development of a visual classification system for wildfire detection. The SVM baseline showed with the same performance, but the vision transformer-based FWSRnet proved superior, reaching 95% accuracy, with an excellent balance in precision, recall, and F1 score. As one et al. In 2024 demonstrated, deploying such models on UAVs allows for real-time detection, which is vital for preventing large-scale wildfires. Moving forward, following the suggestion of Thor et al. In 2020, future research should incorporate adaptive learning to handle evolving environmental data streams, while multimodal data such thermal sensor could further improve detection robustness. I have included the reference, but I can say that as Martinez et al. In 2020 emphasized, preprocessing is fundamental for reliable classification. Jurado et al. In 2024-2025 illustrated how IoT monitoring integrated with AI can improve decision making in real life. Side et al. In 2024 demonstrated the superiority of AI-based computer vision in industrial defect detection. Thor et al. In 2020 provided evidence of the challenges and opportunities in mining IoT data stream for vision systems. Finally, one adult in 2024 showed that UAV-based vision models are effective for wildfire and smoke recognition. In addition, I have this the code that I implemented in Google Colab. I have some descriptions within the code. This is for phase number 2, visual classification for wildfire smoke, IoT and plus UAVs. We have done the preposition, feature extraction, SVM baseline, the BIT training, evaluation, and error analysis. This notebook is structured to mirror the report section and can be used in any 3-stage class imaging datasets, organized as fire, smoke, background folders. We have included the comments done by all the references. We can have the preprocessing, feature restriction, SVM baseline, vision transformer, metric visuals, and reproductivity. So here are the code. I have to set up the environment. We need to configure the paths and parameters. This is the data set. It has been included in the zip file. So I have here the address of the zip file. If needed, you can zip the data set. The data recovery and stratify split. So we have in this small test, only I had used 200 images for smoke, 200 for fire, 200 for background. I had the preposition of augmentation, resizing, normalizing, augmentation, depends. And follows what Martinez et al. Says in 2020. Please remember that we need to emphasize in preposition and transformation. These are the code. So we follow with feature extraction, histograms, LBP, CANI. These feature traits. We proceed to train the SVM baseline using science key learn. Remember that we follow what Jurado suggested. This is the SVM computation matrix. We follow with the vision transforming BIT fine-tuning. Follow what one et al. In 2024 said. We have the matrix conclusion, the training loss, the validation accuracy. And we have done some error analysis. For the example, or for this data set, we don't have any misclassified samples. We have run an inference helper on a single image. This one particular. And we have saved all the information to all the results. And we have the references. So this is basically what you have to do in this learning phase. I will try to share some information with you for you being able to to take some notes on this. That is all for my part. Thank you very much, and have a very good day.